Can't remember. With one group, I remember we finished clock. Did we finish clock? Or we were still talking about it? Did we finish clock? I'm still working on that. Can anyone guide me? Send me a message to let me know where we were. I remember we got started with clock, of course, disk we finished, but I'm not sure with your group whether we could finish the clock and some user interface. Oh, okay. In the last class we did with exercise elevator algorithm, which was good. So now, can you point me? So did we start clock or we just finished the disk? We didn't even start clock. We finished disk. All right. So today we will first talk about the clock. And once we're done with the clock, then perhaps we'll come back to IO. In fact, the IO should have been the first chapter. But anyway, there's no harm, and that's the way we are going with the other groups as well. So we stick to the plan. Thank you. So we will go with clocks. Clocks and user interfaces. A very important chapter. I mean, important and interesting because as we're talking about the clocks, you understand the clock is one of the most important and interesting things. So let's move in and see what we have right here. What kind of interesting things are there? Okay. So what is a clock? These are the one things that we are going to study in this short part. And see, let's see that if we can go to the end of this part as quickly as possible. It's about clock and user interface. The first part, clock, is more important, definitely more important and interesting. But the next part is a little bit of, again, a theory, how some of these IO devices, they work. I mean, at the software level, of course, not the hardware level. The ones that you're talking about, the user interfaces, you can see the input software and output software. For example, input software is the drivers, basically drivers for keyboard, drivers for mouse, and uh, the output software is the monitor software. Okay, there are some special terms there, and those terms we'll have to remember. That's it. And how it works, some very fundamental ideas. What is true font? What is true type font? And what is a bitmap font? And what are the problems? So it's more like trying to remember what is what. But the first part, when we're dealing with clock, is a very interesting part because clock, as we understand, the clock is a hardware. And as at one point of time, I said, if someone asks you that can you tell me something about a computer clock? And if you're a smart guy, then you can always say that, well, what you want to learn about a clock, because we have clock algorithms, we also have clock hardware, and we also have clock software, as you can see on your screen. Oh, by the way, I've forgotten to share my screen. Wait a minute. Early in the morning, forgetting. Just a minute. What happened? There we go. So there we are. So as we said, that we have the clocks and the clock software, the clock hardware. So the one thing important about the clock hardware, because we see that this is uh, in the I/O part, and definitely, and it is an I/O device. Like any other I/O device, what it does is to constantly give an input, or it is giving an input. It's not exactly receiving an output. So it is giving an input in in terms of an electrical pulse, you might say, an electrical pulse. But something is very special about this input device. That's clock. Well, there are a couple of things. First of all, it's neither a block device nor a character device. Now, we don't still know what is block device versus character device, but obviously we will get to know block device and character device in the next chapter, not in the next chapter, in the next part of this chapter, that is the I/O. So essentially, as we understand that the block device are the ones that deal with memory. Okay, for example, disk. Disk is an I/O device which is of type block. Okay, block device, which we put in the category of block device. USB, you might say. That USB is also a block device, your flash drive, where you store your information, the portable one. Then Blu-ray, there's another device, the Blu-ray. So all these are examples of sort of I/O devices. Now, disk, the sort of I/O devices that fall in the category of disk. One is disk spatial device, a disk device. Another one is the character devices. Character devices are usually printers, scanners, keyboard, mouse, where every input or output is based on one single pulse. That is the character that is transmitted. Now, this one, the clock, is neither a block device nor a character device. Yet it is an I/O device. So we need for all these block device and character device, we need a software, and that is usually the driver. Okay, that is the driver software. Here too we have a driver, although we don't exactly call it a driver straight away, but it works. It does work as a driver, and that is the software. Okay, that is the software that works as a driver. Another important thing, another important issue related to clock hardware is the interrupts. Now, we already understand that all the hardware, especially the I/O device hardware, they communicate with the central system through a series of interrupts. We call them interrupts because they are unpredictable. These pulses are unpredictable. Okay? We call them interrupts. The name suggests that an interrupt must be unpredictable. And of course they are, because there's no way that anyone can make a guess or assumption or write an algorithm about when is the next time the user is going to click the mouse or press the key. You can't make a guess on that. So no algorithm. That is the key thing. Okay. The next thing, so all of these I/O devices, they essentially generate interrupts which are unpredictable, and that's why we call them interrupts. But clock is the only one hardware that generates periodic and predictable interrupts, because that is why it is clock. I mean, it just works as we understand how the way the clock works. But the clock hardware generates periodic and predictable interrupts, which then the software will somehow, and we will see what somehow means later. So somehow the software will convert it into real time and hand it over to the computer. Why clock is so important? Clock is so important because one single reason. And a multi-programming computer systems, we understand that a responsive computer system like your PC or your laptop, everything is running based on context switching. These multiple processes are getting switched on CPU. And for that, earlier we found a handful of algorithms, preferably preemptive algorithms. Okay, I intentionally use that word just to remind you, if you can remember, preemptive algorithms. In all those preemptive algorithms, we had a factor embedded inside the algorithm itself, and that was time, or quantum, a slice of time. Right. Now, why it was important? Because if you take the clock out from your computer, then your computer will not have any perception of time. And naturally, if it doesn't understand, it fails to recognize time, then all those algorithms will fail. And if they fail, your computer will come to a standstill. It will not crash or explode, but it will simply come to standstill. That is the problem. That is a problem that will be the problem that if you decide to take out the clocks, computer clocks. There are actually more than one clocks inside your computer, in modern computers, right? So we need to be careful about the significance of the clock. It's not just because the clock will give you the time. Of course, based on that perception of time, there are a whole bunch of other things, including context switching, as I've pointed out right now, they are being performed and they are being controlled. So naturally, we need to be careful about these little things. That is one of the most important things. That is the significance of what we call the clock. So now that we understand what the clock is all about and how it is supposed to work, so we will move in to see how they work and also the duties of the software. So we have in the clock part, as we can see, the clock hardware, the clock software, and also clock soft timers. So let's dive in and see what else we can find right in there. Overview. It is a timer. Well, it is. It is a timer because that's the way it works. That's the way it works. Okay. Remember, when we use the word timer and when we use the word clock, in our mind, we have two different perceptions. When we use the word clock, that definitely kind of gives us an impression of some kind of hardware, right? But when we see the timers in normal conditions, I mean, in general, not about a computer clock, we think about the implementation of the hardware. Think about it. So basically, what I mean, that you have the hardware, and then you set up the timers, and you keep waiting until each of these timers expire, for example. So with time, you set the timers. So it's more about the clock gives us the time, the perception of time, and those times can now be utilized by setting up timers in whichever way you interpret them. So essentially, that is what OS is doing. In the long run, we'll find that OS, for a whole bunch of activities that it does with the clock, not only context switching, but at the micro level, for example, about registers, CPU actions, many of the CPU actions, process behavior, everywhere we need the concept of time, to use the perception of time. And wherever we need them, OS sets up timers. They're essential to the operation of a multi-programming system, no question about that. We have already mentioned why, mentioned the time of the day, and prevent one process from monopolizing the CPU. Essentially, what we have already learned is context switching. And that happens along with the preemptive algorithms. We had a bunch of preemptive algorithms, and most of these algorithms will fail if your computer doesn't have any notion of what time is. So that is the problem. Another important piece of information that you get here, so I think I mentioned at the beginning, is the clock software takes the form of device driver, even though a clock is neither a block device nor a character device. It takes the role, so we just can't say it's a driver, but it does take the role. And obviously, it comes from the same source. That means the clock vendor, the hardware vendor, will give you the software. Very similar to the driver. Structure. So what is inside the hardware? The hardware, the clock hardware, is essentially a pendulum. Okay, many of you, you're not familiar with this word. Or an oscillator. So just imagine the pendulum thing. You hang a string and you hang a ball. In fact, you see it, some old-fashioned wall clocks, you see the pendulum constantly, let's call pendulum constantly moving from this side to that side until it comes to a standstill. It's a very similar concept, but here it is oscillating. Oscillation means this movement that it is taken, say, for example, distance n, and if you let it go, it will go all the way to distance n on the other side, and then it will swing back, right, to this side, this time a little less, n minus 1, and swing back to the other side, the same distance, n minus 1. So that's the way these oscillations, these are called oscillations, and these oscillations will keep going and going until it comes back to standstill. It comes to standstill, that means it comes back to its original position, a stable position, let's say, where basically the displacement is 0. When it reaches there, it generates an interrupt. That is when an interrupt happens. In the case of keyboard, when you press the key, the interrupt happens. In the case of mouse, when you click the mouse, you generate an interrupt. But here, it is when the oscillation stops. At the end of one full oscillation cycle, you get one interrupt. And that cycle requires a very tiny amount of electric power. That is a cycle of 50 to 60 hertz. So naturally, your computer clock is ticking even though your computer is shut down. I mean, the hardware part is still going on. Okay, not the software part, no question, because your computer is shut down. That means the RAM is free and nothing is there. Clock software is just like another software. So it is not working when your computer is shut down. But your hardware still keeps ticking. So that is exactly what happens. In fact, later we'll see that we can actually use the software to control how much power needs to go there to generate an oscillation. In fact, we can control the perception of time. That's one of the things that we can do by using the software, because software needs to know exactly in terms of time, that how much time was spent to complete this one single oscillation cycle for each interrupt. It's an interrupt. So what else we have? Let's take a quick look at it. This is what we have, but not this one. This one is just a picture. Inside the hardware, this is important that you need to remember. We have three things: a holding register, a counter register, a counter, and the oscillator itself. Oscillator is a crystal quartz, and that's why we use crystal quartz, because it needs a very little amount of energy to keep oscillating. How do we use this holding register? The holding register is a kind of permanent copy, and this one is more like RAM. If any of you struggle to understand how they work, just think about it that this is your hard disk. Everything is stored here as a permanent way. And every time you want to use them, you must load it right here on RAM and use it. It's just a quick analogy. Okay? I don't say that this is counter register is RAM. Yeah, it's just an analogy. And that's exactly what we do. In the holding register, we all have the values like n -1, n-2, and also similarly right here on the left side, n -1, n-2, something like that. Okay. If you think about this being the central position. So every time you want to go ahead with another round of oscillation, you have to load these values straight in the counter, and then get the oscillator started. And the oscillator will read from the counter, as you can see, and it will keep oscillating, oscillating, oscillating. It will just follow the counter. Just don't follow the holding register. The holding register, for good, it holds these displacement values. That is how it works. Now, clock hardware can actually work in two different modes. The first one, the first mode to work in is what we call one-shot mode. In one-shot mode, basically the oscillator keeps oscillating. The first cycle is over, and when the first cycle is over, it generates an interrupt, and when it generates an interrupt, it stops. The clock stops until the software explicitly starts it all over again. It could be a delay, the first interrupt and the second interrupt. It all depends on how software behaves and when software wants to start it. So basically, software has a greater role to control it. Well, most of the modern computer clocks, they work on square wave mode. So one-shot mode doesn't really give the perception of real time to a computer. But that's one the square wave does. Square wave simply means when the first interrupt happens, then the oscillator comes to a standstill. Now the counter buffer is now empty. Immediately, it will get automatically reloaded. All the values from the holding register will get reloaded in the counter for the next round of oscillation. And these oscillations will keep going for an indefinite period of time. So that is exactly how this clock software works, the clock hardware works. As you can see right here, it's important. This too, what is one-shot mode and what is square wave mode. Okay. So the one-shot mode and the square wave mode, they keep oscillating in that way. In a square wave mode, that is more beneficial. So this is the first one, as you can see, the one shot mode. The clock is started, copies the value of the holding register into the counter, and then decrements the counter at each pulse from the crystal. So when the counter gets to zero, it causes an interrupt and stops. And that is what we call an interrupt. But when we introduce the square wave mode, we get periodic interrupts, not just one interrupt, not an interrupt, periodic interrupts. These periodic interrupts are what we call clock ticks. But clock ticks doesn't mean that it is equal to it or it equals to 1 second or 1 nanosecond or anything. It has nothing to do with the real time. So advantages, its interrupt frequency can be controlled by the software. 500 megahertz crystal is used, then we see that 2 to 8.6 nanoseconds. So at least now software understands that on an average how much time it takes to perform one single clock tick. That means one cycle of oscillation. Okay? So if you get to that point and you collect a bunch of clock ticks and you know the time, precise time taken by each of these clock ticks, okay, on average. So it's easier to calculate the real time, right? And that is what they are doing all the time. That is
Hey, Papa, look. Look.
So that is what we are doing. So all the clock hardware here is generally interrupts and known intervals. Everything else involving time must be done by the software or the clock driver. Okay. So clock hardware generates the interrupt, and the clock driver of the software will do the rest. Now let's dive in to see what are the responsibilities of the software. This is important, and that leads to the highlights of that. The first thing is how it calculates the real time. Okay, rather, of course, we know how it calculates the real time, but it's about maintaining the real time. Maintaining literally means that, as we know, you keep your computer shut down for 24 hours. The next day you open it, and you still get to see the correct time and date. I mean, the current time. It displays the current time. Although we understand the clock was literally dead, the computer was shut down. So we understand the hardware was probably still ticking, but software is definitely dead for 24 hours. But how does it keep track of that? Well, there are quite different ways to do that. The first thing we did was to start from a historical point of time. Well, what do you mean by historical point of time is like at the time when your computer got started as a computer. Okay, in other words, the computer was assembled for the first time. Then probably at a historic date, that is the 1st January of 1970, for example. And that's when the computer was manufactured. Everything was set up, and since then, they all started working together as a computer. Now, and we use 32-bit. So basically, we were storing all the bits, all the clock ticks into 32-bit counter. Okay, starting from a historic date. So whenever we needed the time, whether the computer is on and off, when it's switched on and switched off, doesn't matter. Whenever we needed time, we were always collecting those clock ticks. And whenever we needed time, and obviously the computer must be on at that point in time, all we have to do from time to time, the software will just do the simple calculation because it has a whole bunch of clock ticks. All it has to do is divide it with the exact time, and that's it. It will get the perception of time, and it will display it on the screen straight away. But one of the problems with that is we saw that the 32-bit register will just simply overflow in over 2 years' time. After 2.5 years, it will not work because simply it is overflown, the 32-bit register. So we tried to introduce 64-bit, which is quite expensive and not a reasonable solution, using 64-bit counter. Then we had another approach where things were made more complex, like maintaining the time of days in seconds rather than in ticks, okay, using a subsidiary counter to count ticks until a whole second has accumulated. So if we try to do that, then at least we survive 136 years. So basically what to say is we say that one clock tick, now here we are storing the ticks, right? If you think these are all clock ticks. As we saw, the one clock tick is kind of like 2 to 8.6 nanoseconds, right? Nanosecond. So basically to store 1 second worth of clock ticks, right? You literally have to store 1,000 or 10,000 or more. Okay, at the nano level, you can understand how many clock ticks you will have to store, right? Just to save 1 second. So that's why we did that. We didn't save all the clock ticks as we're doing right here in the old model. We converted them into seconds, and then we stored the seconds. So that is maintaining the time of the day in seconds rather than in ticks. Okay, we were always using them in seconds, and we were maintaining it. It could last 136 years, but that is the maximum number of seconds that it could, 2 to the power 32 seconds, it could store. But then after that, there will be problems. So the third approach is the most feasible approach that we have adopted. And the part of this approach is all about a simple trick that we play. What we now do is still get back to 32-bit register because that is cost effective, but we are not storing everything from a historical point of time. In the first place, we made a mistake by trying to store all the clock ticks from a historical point of time. So what we now do is we still have 32-bit register. We do it relative to the computer's last boot time. So say, for example, when it was last booted, in fact, it was shut down, the computer was shut down. Say, for example, it was 4 p.m. when you shut down your computer. So after the computer has been shut down, the software is dead. Obviously, no question about that. But the hardware is still ticking. So basically, you are getting a bunch of clock ticks only. But those clock ticks can't be converted by the software into real time during that shutdown period. You kept it shut down for 1 hour, and at 5 p.m. you restarted it. In between 4 p.m. to 5 p.m., our 32-bit register will store all the clock ticks that happened during that period. It's easy, no problem, just a matter of 1 hour, right? It could be 2 hours, it could be 3 hours, it could be 24 hours, no problem. So it's stored right there. So, and before the computer actually was shut down, the real time of the computer was also saved. Real time was saved. So the real time was saved, and the computer is now shut down. Nothing is working in terms of software except the hardware, the clock hardware that keeps ticking, and a bunch of clock ticks have been accumulated over the next 1 hour. 1 hour later, you reopen it or restart your computer. As you restart your computer, you, of course, keep the software running. And as the software starts running, software will pick up these two things. One is this one. Okay, the real time, the last booting time, and it will have a bunch of clock ticks, accumulated clock ticks from the register. It will just convert them into real time. So after conversion, it gets 1 hour, and 4 p.m. was the last saved boot time plus 1 hour. So current time is 5 p.m. It generates and it displays to you. Easy. But the only point is, as we know, the 32-bit register won't survive more than 2.5 years. Okay. So essentially, if any of you keep your computer shut down for 3 years, for example, and 3 years at a stretch, you didn't open it, and maybe you went abroad and spent those 3 years elsewhere, and then after spending 3 years, 5 years, you came back and you wanted to start your old computer. You will have to, if that is the case, you will have to reset the clock. And you know it, that we have to do it. But when you are using a computer in general, a general purpose computer, an utility device that we need to use off and on, well, we don't usually keep it shut down for 2 years or 3 years at a stretch. Do it. No. If we do it just in case we have no other choice but to do it, then of course rest assured that when you restart your computer after 3 years, you will have to reset the clock manually. The clock will not give you the correct time. So that is what we understand about how the basic thing of the software, the maintaining the day of the time, the real time, works. Apart from that, the software has many other duties. And I advise you to remember all these duties, at least the headlines, because sometimes they quote the headlines and they'll ask you, so which of the following are the duties of the clock software and which of these are not? So that kind of tricky questions they may ask. The typical duties of the clock driver, one of the things is, as we said, it prevents one single process from hogging the CPU. In other words, it helps in context switching in a multi-programming environment. The preventing processes from running longer than they're allowed to. When a process is started, the scheduler initializes a counter to the value of that process's quantum in ticks. At every clock interrupt, the clock driver decrements the quantum counter by 1. When it gets to 0, the clock driver calls the scheduler to set up another process. Okay, so that's the job. Process from running longer than they are allowed to. And how do they do it? The software itself has a kind of timer. Okay, not a timer. It's a counter, because the software is a counter in clock ticks. Because most of the algorithms that I was referring to, like, say, for example, round robin algorithm, there we mentioned something called quantum. And this quantum is usually a slice of time is maintained in clock ticks. So the software can directly work with them. And the software's job is to activate the scheduler, alert the kernel about activating the scheduler when the time of the counter expires. Okay, it sets a counter, which basically works like a timer, but we are not using the word timer in this case simply because we are still dealing with clock ticks. And we know the clock tick is all about interrupts. It's a mechanical interrupt generated by the hardware, nothing more than that. So that's the reason we're not using the word timer. But timer we'll be using later on when the software has actually converted these clock ticks into real time. We'll be using timer, the word timer. When a process starts, schedule initializes the counter to the value of the process quantum in clock ticks. Clock interrupt, the clock driver decrements the quantum counter by 1. If it gets to 0, the clock driver calls the scheduler to set up another process. Easy enough. Accounting. The two ways of accounting of CPU usage. You need the perception of time. So the whole point, the first approach that we have is using a second timer, which is distinct with system timer, to calculate how long the process has run from the point process is started and needs to be stopped. The second approach is too expensive and rarely done. A less accurate but simpler way to do accounting is to maintain a pointer to the process table entry for currently running process in a global variable. At every clock tick, a field in the current process entry is incremented. I don't have to go into details of this, but just remember the accounting of CPU usage, just like preventing processes from running longer than they're allowed to, is another core responsibility of the driver or the software. Another one, handling alarm calls. This is alarm system calls made by user processes. A process may request that the OS gives it a warning after a certain interval using a signal, interrupt, messages, whatever, an acknowledgement signal. To implement, a table is used to keep the pending timers. A table is maintained as well as variable, giving the time of the next times. Whenever the time of day is updated, the driver checks to see if the closest signal has occurred. If it has, the table search for the next timer to occur. So that is what we do. Providing watchdog timers for parts of the system itself, that is another one. OS also need to set timer to cause an interrupt after a sufficiently long time interval. So that is what it does. Doing profiling, monitoring, statistics gathering, OS provides a mechanism by which the user program can have the system build up a histogram of its program counter. So that too, by itself, is one of the responsibilities. So all you need to do is to remember these core responsibilities that they are mentioning right here. That is So the watchdog timer is another one where for part of the system, OS also need to set timers to cause an interrupt after a sufficiently long time interval. Doing profiling, monitoring, statistics gathering being another important duties. So we do have the whole bunch of things right in there. So try to remember the main duties, as I say, of the typical duties of your software, because these are some of the things they ask. They don't go into the details of it, but they will just ask you to pick up the odd one, or they'll just mix it up with some odd ones, and they ask you to pick up the correct one. As I said, the OS does everything with one single thing, one single perception, and that is soft timer. Because the OS doesn't want to make things too complicated. Because OS has a lot of other jobs to do and things to take care of. So it is not possible for OS to pay attention to all these tiny responsibilities, little responsibilities that you'll have to deal with. So basically what OS does, it sets up a bunch of soft timers. Now the way the soft timers work and why it is so important is basically because they help the OS to avoid interrupts. Now, if you didn't have the OS, you didn't have the soft timer, then obviously you are supposed to interact with, you're supposed to get the interrupts, right? Respond to the interrupts coming from the clock. But now, so just try to imagine that this is your OS. And here is the user mode, and here's the kernel. So OS is constantly switching back and forth. That's what we understand. The user process is running there in the user mode, and from time to time asking for kernel services for whatever reason. Right. Anything that is running, that when OS, if you keep the OS busy in the kernel mode, we already know that will slow down the machine considerably. So what can we do? Because if you are generating periodic interrupts, remember, clock generates periodic interrupts. Periodic interrupts. So if there are periodic interrupts, these periodic interrupts will keep the kernel busy. That means the OS will never ever have a chance to spend a good amount of time taking care of the process in the user mode. It will always have to, for each clock tick, every 2 nanoseconds, it will have to switch back to the kernel mode. That is not welcome. That is not welcome. So what we do, we don't want it to switch back like that. We want to avoid unnecessary switching of the OS into the kernel mode. And how can we do that? We can do it by using the soft timers. The OS as we will see, the OS will set up timers for all important events and actions. To set up timers for all the important events. And these timers will expire at the moment the OS is in the kernel mode. So basically, OS will set it up, like say, for example, timer 1, timer 2, timer 3, and timer 4. It doesn't have to come back to this kernel mode all the time to keep checking these timers. So they are in the kernel whenever OS is already in the kernel mode for any other reason, because there can be many reasons because of which the OS will have to switch to the kernel mode. Before it goes back to the user mode, it will check this. It will check these timers. Any of these timer is already expired, then that task will be performed. If not, then it will simply switch back and wait until it has to switch back again. So basically, for these actions, this is a little bit of a risky thing, but it works in that way, because the risky in a sense that some of the timers may actually fail. The soft timers may actually fail. Fail because it will fail because if the kernel doesn't have, the OS doesn't have any reason to switch back to the kernel mode. As we can see, it's an OS facility that allows efficient scheduling of software events at a microsecond granularity. Whenever the kernel is running for some other reasons, just before it returns the user, it is very important soft timers. The kernel is running for some reason just before it returns the user mode. It checks the real-time clock to see if a soft timer has already expired or not. If the timer has expired, the scheduled event is performed, with no need to switch into kernel mode since the system is already there. As in the case when the system is already context switched to the kernel, why not see if other work can be done while you are in there? After performance, the soft timer is reset to go off again. All that has to be done is copy the current clock value to the timer and add the timeout interval to it. So that's all you have to do. The soft timers stand and fall. This is an important piece of information that you're looking at. With the rate at which kernel entries are made for the other reasons. As I said, that it's your luck that if there are system calls, plenty of system calls, then it will have to come back to the kernel mode. And if it comes back to the kernel mode, then before it goes back to the user mode, it will check the timers, the soft timers, and will do something. TLB misses is another reason because of which the page fault happens. and the OS will have to switch back to the kernel mode. Page faults, another reason. I/O interrupts, the kernel, the OS needs to be in the kernel mode, and the CPU going idle. So the rate of these happening in turns makes standard fault. Okay, so that is essentially what it is. We understand. Okay. Once we understand the soft timers and what they mean actually, that they fail and how do they fail, once we understand that, then and we will go down, we'll go to the next part. That is the keyboard software and the user interface. Keyboard software, in the keyboard software, we have the scan code that we usually use. Keyboard software that uses the scan code, the number in the IO port represents 7 bits. As I said, in this part, it is all what is what. 8 bit is used to represent the key press, 0 or 1. Usually, it's the responsibility of the driver to figure out whether it is the uppercase, or the lowercase. So that is what it does. In keyboard software, a couple of things, echoing, the new words. Many users have been accustomed that echoing literally means that when you are pressing a key and you do expect that it will appear at a certain point on your computer screen. Okay. So that is what we call echoing, that how many spaces that it is going to echo or jump. Many users have grown to just appear on the street, but it is more complicated because at the very least the keyboard driver has to figure out what to put the new inputs without being overwritten by program output. You don't have to go deep inside to know exactly how it happens. It is just remember the name, echoing. That should be enough. In tab handling, what we need is basically you have to take echoing and have to compute the proper number of spaces that needs to be echoed. Okay. For the output from the program and the output from echoing, you have to take both these into consideration so that they don't superimpose each other. Another one thing is device equivalence. Here you are again finding some important and interesting words. And what are these important, interesting words that you have right here is, for example, carriage return and a line fit. Okay, to advance to the next line. So carriage, you have the carriage return and the line fit to advance to the next line. Carriage return and the line fit. So when the carriage return, what exactly carriage return means? Carriage return means when you are typing something in the line, you go to the end of the line, then you get a carriage return. Carriage return will bring you back to the start of that line. This position is called the carriage return. Okay, this is where you get started. And then this is where you get started, the carriage return. And then from there on, that you have to go back to, this is the carriage return. And after that, what you'll have to do is you need a line feed. So basically, line feed and carriage return, they go hand in hand. The line feed will take you to the next line. So basically, your carriage return will get you back to the first column, the start point, and then line feed will take you to the next line. So your cursor is positioned at the beginning of the next line. That is what we do. The internal convention, the monitor may require both a line feed and a carriage return to be echoed in order to get the screen updated properly. Sure. So these are the things that we really need. Another one, we'll just quickly pass through it, mouse software. Whenever a mouse is moved a certain minimum distance in either direction, a button is depressed, released, a message is sent to the computer. Okay. Now it basically sends two messages. The change in X position since the last message and the change in Y position since the last position since the last message. The status of the buttons, and that's what we do. The message usually occupies 3 bytes containing 3 items. Mickey is a unit representing minimum distance, about 0.1 millimeter of displacement of the cursor. Most mice report back at maximum of 40 times per second. Mouse only indicates changes in position, not absolute position itself. Sure. The changes in position, as you could see right there, change in X position. The single or double click is distinguished by the software settings or by the driver. These are the bunch of information that you will have to remember from the mouse part. There's nothing much in it. About the text windows, the program sends characters to the characters current windows, and they're displayed there. Usually a character is written in one system call. Screen editors and many other sophisticated programs need to be able to update the screen in complex ways, such as replacing one line in the middle of the screen. Driver must support escape sequences to move the cursor, insert, and delete character. The screen editors and many other sophisticated programs need to be able to update the screen in complex ways, such as replacing one line in the middle of the screen, and the driver must support the escape sequence to move the cursor. Well, there are a whole lot of things, but the things that will be useful for, say, from your exam's point of view. For example, WIMP, the Windows Icon Menus and Pointing Devices. These are some of the names that we are familiar with, and they usually contain a graphic adapter or a video RAM to hold that image. We understand what is Windows. The basic item, the screen's rectangular area, and in terms of X and Y coordinate, the top left corner is the 00, as you can see right here. Okay. The last one is the bitmap. Bitmap is basically, if you use the bitmap, we understand the problem is this, that if you zoom it or if you expand it, then it gets, you raise the font size, it gets pretty much pixelated. Okay, so how can we address the issue? To address the issue properly, we have the bitmap font that doesn't work. We have TrueType fonts. I've just highlighted some of the important things right here. TrueType font was first invented by Steve Jobs. So what they do, they measure from there. This point is 00, and they have given all the data points, coordinates of all these elements. And they will simply, when you raise it, they will raise it by 3 times. Say, for example, you want to enlarge it. So once you enlarge it, it is uniformly enlarged. So that is essentially what they do. Each TrueType character is defined by a sequence points around its perimeter. All the points related to the 00 origin. It's easy to scale the characters up or down with any point size, even fraction. All that has to be done is to multiply each coordinate by the same scale factor. Okay, so that is what we do. In this chapter, as I said right from the beginning, there's nothing much into the second part. It's all about just a quick read. But the clock, also, there are a lot of things to remember. But essentially, what is the clock, the hardware and the software, what is inside the hardware, that's important, and how it works, the clock ticks, the periodic interrupts, and what does the software, in how many different modes the clock hardware works, and finally, the software. What are the core duties of the software, and how does it maintain the current time and date? Okay, these are some of the core things that we will have to pay attention to. All right, that's all. And so in the next class, we will get started with I/O. Again, a little bit of theory, but still interesting. A little bit more interesting. Xuan Wong, usually you're the one sending message. Okay, here we are. Ji Kang,
Yes.
Ren Phuc, Ren Phuc, the candidate. Oh. Duc Wong,
Yes.
Luong Ha,
Yes.
Lu Wong,
Yes.
Chan Hum,
Yes.
Nop Phat,
Yes.
Ben Min,
Yes.
Quoc Huy,
Yes.
Hoai An,
Yes.
Kim Thuc,
Yes.
Nhật Minh,
Yes.
Hiền Phúc, Hiền Phúc, Quang Huy,
Yes.
Min Quang,
Yes.
Duy Bao,
Yes.
Quay Min, Liam Chuk, Quoc Hung,
Yes.
Hiền Phúc. Okay. Thank you. That's all. And keep preparing.
Papa, I'm going to do that again.
All right. So that's all. And we will see you again in the next class. So keep preparing for your presentation. That is.